Hi. So the objective of this video is to piggyback off of the concepts that we discussed in part one. In this video, what I want to do is go over some examples and then talk about the Maclaurin series a little bit and what the differences are, even though they're very subtle. So what I have on screen right now is the Taylor series equation, which says that f of x plus h is equal to f of x plus f prime of x times h plus f double prime of x times h squared over 2 factorial, etc. We'd have f triple prime h cubed over 3 factorial, and so on. And what we're saying is that we are interested in some unknown point, x plus h, and we're going to try to estimate what that y value is by knowing and using the behavior of a point that we do know. So in this picture here, let's say that x is the point that we know. And maybe we know the function value there, we know the first derivative there, we know the second derivative at that point, and so on. And based on all of our knowledge, we can go ahead and predict where the function is going to end up h away from that point. And we discussed in the previous video how you would need an infinite amount of terms to exactly give the value at this point h away. But in many cases, we don't want to have an infinite number of terms. It takes a lot of time. So maybe we only use a few terms. And we discussed how, depending on how big or small h is, that will end up dictating how accurate of an estimate we have at this new point x plus h. And I want to do an example to kind of illustrate that. And if you're in my class, this is going to be very similar to the example that we did already in the note set for Taylor series. And I tell you that I want to find the value of cosine of 2, where this 2 is in radians. And I want you to find that estimated using a 3-term Taylor series. Or 4-term Taylor series. So we're trying to estimate cosine of 2. We don't know what that value is. That would be the left-hand side of this equation. So let me go ahead and copy this so we can use it again and kind of compare. In our example, f of x is cosine of x. And I'm interested in knowing what is cosine of 2. That's basically our ending point that will be h away from some other point that we already know. So we need to determine what our reference point is, or our known point. And ideally, we pick something that's pretty easy, because if we have an easier right side to evaluate, then that makes our lives easier. And depending on the known point we do, that'll be some distance h away from 2. Let's see if we can put into math what I'm saying. So basically, f of x plus h, this is going to be some cosine of 2 is equal to some stuff that we have to figure out based on our reference point. And an easy value of cosine that we can do is assuming that our known point is at x equals 0. If we assume that that known point is x equals 0, what we can do is look at this again And if x is our known point, what this will be would be f of 0 plus f prime of 0 times h plus f double prime of 0 times h squared over 2 factorial plus etc. And my f of x plus h, the thing that I'm looking for is f of 2. I'm interested in cosine of 2. I'm going to use cosine of 0 as my known point in order to estimate what cosine of 2 is. So if we compare, let's draw a picture maybe to try to visualize what's happening here. I know what f of 0 is. If we do cosine of 0, we know that that is 1. So we know that cosine of 0 is 1. And I don't know what f of 2 is. I'm trying to find that. But what I do know is that the point I'm trying to find, this is an h of 2 away. Because remember, we have a point x that we know. The point we're looking for is h away from that point. In this problem, we're interested in x equals 0 and x equals 2. The distance between them is 2. Therefore, this is our value of h. So we're going to say that f of 2, or cosine of 2, this is going to be, well, I guess instead of doing this, let's first think ahead. In this problem, we're interested in the function value at 0, which we already know is 1. We also need to know what is the derivative at 0. What's the second derivative at 0? And since I said 4 terms, perhaps I'll include that fourth term, plus f triple prime of 0, h cubed over 3 factorial. We need that derivative as well. We need all of those function values in order to estimate what's happening at x equals 2. So if f of x is cosine of x, I know that f of 0 is cosine of 0. That's 1. Okay, we got that. Fine. Let's go ahead and take derivatives. The derivative of cosine of x is negative sine of x. That means that the derivative at 0 will be negative sine of 0. Sine of 0 is 0. Negative sign doesn't matter. We see that that first derivative term is 0. We'll go ahead and find our second derivative now. Derivative of negative sine of x is the same as negative cosine of x, which is f double prime of 0. That's going to end up being negative 1. I guess I'll be really thorough here. Negative cosine of 0 is negative 1. And we have to do one more, but as you'll see, this will end up being a function of sine. This is just sine x in this case. And I know that if I plug in 0 into sine, I will get 0. So looking at these different terms, let's go ahead and erase these colors. F of 0 is 1. F prime of 0 is 0, so this whole term is going to go away. F double prime of 0, this is negative 1. And then f triple prime of 0, we just said down here was also 0. So all of these terms go away. So what we're going to do now is actually use this to our advantage. F of 2, scroll back up, and I'm going to go ahead and just copy some of this stuff. I'll erase it in a second to make it look prettier. Things we're going to erase are the 0 term, the 0 term. This is essentially what we're working with. What this means is that f of 2 is going to be 1 plus negative 1 h squared over 2 factorial. And then the other terms were 0, so those go away. We know that h is 2, so this is 1 plus negative 1 times h squared, which would be 2 squared, over 2 factorial. This is going to be 1 plus negative 1. 2 squared is 4. 2 factorial is 2. This is the same as 1 minus 2. So our function at x equals 2 is negative 1. So f of 2, which is the same as saying cosine of 2, is approximately negative 1. And we're interested in how good of an answer that is. Let's say that we actually compute the true value of cosine of 2. So the true value we can do in our calculator, that will be cosine of 2. The true value is exactly or approximately negative 0.1 or 416,147. And this thing that we just found, this negative 1, this is our approximate value from the Taylor series approximation. If we were to find our relative true error, we know that this is going to be the true value minus the approximate value over the true value. If that is a percentage, we'll multiply by 100%. If we do that calculation, plugging in the true value, which again is this, that's the true value, and then plugging in the approximate value into that equation, we get something like 140%, which is a pretty large error. Why is the error so large? Well, what we'll see in a second is because the h, the distance between 0 and 2, is pretty big compared to what we can possibly use. So if we come back up to this picture, we see that we ended up getting a value, our approximate value being negative 1. So really, it's all the way down here. And this h being 2 is pretty large. So that doesn't help us. Let's do one more. Let's choose a better point. And a closer point to 2 that we know about is pi over 2. So let's choose now our known point to be x is equal to pi over 2. And if we do pi over 2 is something like 1 point something. Let's go ahead and take a look at what that is. Pi divided by 2 is 1.57. 5708 approximately. So if I were to draw a graph, we just did before our x equals 0. And I'm interested in what's happening at 2. For this problem, I'm going to say, let's choose an x equals 0 that's 1.5708. The h value between 0 and 2 is pretty large compared to the h value between pi over 2 and 2. If we look at that h value, that's something like 0.4292, which is smaller than 2. And because the h is smaller, if we look back up at our original Taylor series definition, small h means that these terms over here, these higher order terms, will become smaller and smaller as we go higher in derivatives because of the fact that we are multiplying by h squared. If we have a decimal, and in this case h is a decimal, when we square it or cube it or raise it to the 4th power, we are going to lower it. And that's really big for us, because that means that those higher order terms we can neglect and still have somewhat of a decent approximation. So we'll choose x as pi over 2. And we're going to do the same exact procedure. We already have our derivatives from before, but I'll just rewrite them out again. Same exact thing I wrote before. I'm just finding those first 4 terms in the Taylor series. And if I plug in pi over 2, which is the same as 90 degrees, cosine of 90 is 0. This is going to be, maybe I'll write cosine of 90 or cosine of pi over 2. This is going to be negative sine of pi over 2. Sine of pi over 2 is 1. With the negative sign in the front, this becomes negative 1. Negative cosine of pi over 2 is 0. And then sine of pi over 2 is positive 1. So now I have a similar situation where some of the terms are 0 and the other ones are 1 or negative 1. So what we're going to do is say, okay, f of x plus h, which is again going to be f of pi over 2 plus this h value we had, which is the 0.4292. This is the same as f of 2. That's what we're looking for. That cosine of 2 is what we're interested in. So this thing is going to be f of pi over 2 plus f prime of pi over 2 times h plus f double prime of pi over 2 times h squared over 2 factorial plus f triple prime of pi over 2 h cubed over 3 factorial. So we know from before, from up here, that f of pi over 2 is 0. That's going to go away. F prime of pi over 2, this term is negative 1. So this whole thing is going to be negative h. F double prime of pi over 2 is 0. So this is going to go away. And f triple prime of pi over 2 is 1. So it's going to be plus h cubed over 3 factorial. And again, let's keep in mind that these are approximations, since we have neglected the infinite amount of terms. We've only kept 3 of them, or 4 of them. So this means that our function value is going to be negative 0.4292 plus 0.4292 cubed over 3 factorial is 3 times 2 times 1. That is 6. If we go ahead and do that, we get a function value that is approximately negative 0.416023. This is our approximate value. And our true value of f of 2 was negative 0.416147, as we saw earlier. These are much closer together compared to what we got before. If we were to do our relative true error, this ends up being around 0.030%, which is really good. That's a lot better than our 140% that we had before. And the main reason for that is because this point that we chose, pi over 2, is much closer to 2 than 0 is. So that is what we are doing with the Taylor series, is that we have some known point, we plug it into the function and its derivatives, etc., to approximate what's happening at a point farther away. That's just a quick example. When I say quick, I mean 26 minutes quick. Thank you for watching. The last thing I want to talk about is the Maclaurin series, which won't take up too much of your time. It's just a specific case of the Taylor series. Like I said at the very beginning, our Taylor series is based on some known point x. And that could be any point that you happen to know. That could be any point that we know. Delete that. Delete this, delete that. Okay. In the case where our known point is chosen to be 0, like it was in the first iteration of that example where we said that let's choose x is equal to 0 for cosine of 0. That situation is what we call a Maclaurin series. So when x is equal to 0, and this is the known point, this is a Maclaurin series. The benefit is that if we were to look at a graph and we use the known point of x equals 0, any point I find relative to that will be some h away, right? We're looking at f of x compared to f of x plus h. If x is 0, then we are looking for functions at some h away. It's the same as 0 plus h, or f of x plus h type of thing. What's interesting is that this is on the x-axis. We know that. And since we measure everything on the x-axis from the origin, and in this case, h is measured exactly from the origin, we can replace h with x to basically take it a function and express it as this infinite amount of terms. So really, if I were to just take the same exact picture and say, okay, here's some known point, I'm going to use the Maclaurin series to approximate some point later on. This point's distance away is x, just because we're measuring it from the origin. And the quick example I'll do of that is just to say, let's look at the Maclaurin series for e to the x. I'm not trying to find a specific point. I'm just trying to express this exponential as an infinite sum of terms. If we look at the Taylor series, keep copy and pasting the same thing. If we look at the Taylor series, when we do Maclaurin, what we're saying is that f of 0 plus h, this is going to be f of 0 plus f prime of 0 times h plus f double prime of 0 times h squared over 2 factorial, etc. For e to the x, what's really nice about it is that this is equal to f prime of x, f double prime of x, etc. because of the fact that the derivative of e to the x is itself. And if I plug in 0 into that, which will be the same for all of the derivatives, those are all equal to 1. E to the 0 is 1. So what this means is that f of h is going to be 1 plus 1 times h plus 1 times h squared over 2 factorial plus h cubed over 3 factorial. Let's zoom in and make this a little bit easier to read. Plus, etc. And this is our answer, but typically how you'd see this is since our known point is 0, and we're just looking to see what the function is at any h value away, that's equivalent to saying where is our function at some arbitrary x away from the origin. So we can write this as say that f of x is 1 plus x squared over 2 factorial plus etc. This x is not the same as the known point x chosen to be 0. That's been replaced. This is just a change of variable to say that instead of using h, which is the distance away from the origin, let's just replace that with x to make it the most general case. So now if I have e to the power of 3, I can plug in 3 for x here. And then depending on the number of terms I have, could lead to a very accurate approximation of e cubed in that example. I hope that this helps tie things together with video number 1. If you have questions, please let me know. Otherwise, I'll see you next time. Thank you. Bye.